The Jeffcott rotor model was developed in 1919 in order to replace the Rankine model, and it was significant because it predicted supercritical speeds of rotating machinery, which had been demonstrated to exist by the Laval turbine, although the Rankine model did not predict them. To set up the model, you can make a couple assumptions. First, the shaft is simply supported on both ends with length L, and that the shaft is massless and flexible. And then you also assume there's a disk mass located in the center at L/2 with eccentricity E. And then doing this, you can write Newton's law for the x and y directions, write out the equations of motion, and end up with a 2-degree of freedom system. And then if you assume that there's no damping, then you can uncouple both of the degrees of freedom, and you simply have two differential equations that you can solve each in the time domain and frequency domain. Doing that, you can obtain the amplitude of the amplitude equal to the mass times the eccentricity times omega squared divided by k minus m omega squared. And then in the time domain, these simply become the amplitude times cosine omega t or sine omega t, depending on the direction. And in order to check the model, I was able to do amplitude sweep in the frequency domain for different parameters, and was able to confirm the natural frequency. And I was also able to plug in the original numbers that Jeffcott used in his original paper, and came up with the same values.